One thing we can do with complex velocity potentials is actually translate and rotate them within the domain, and we'll find that this is really useful. So let's look at an original complex potential. We're going to call this phi 0, and this would be some solution in this real and imaginary plane. Okay, so we've got phi naught as this original solution, and now we want to translate that solution or translate the potential element. Let's say we've got some potential element here at the origin, and now we want to look at the flow field if we were to translate that to another point. And that point we're going to call Z0, okay? And this new potential we're going to call phi of Z. This is our real capital Phi of Z. We had some phi naught over here on the left-hand side when our potential or elementary potential flow was centered at 0. And now we want to look at the flow field. If I move that potential element, whether that's a vortex or a source or a sink or a doublet or whatever it is, when I move that to another point, I want to see what the flow field is going to be as a function of z. Okay, so what we might realize is that the flow at some location relative to z naught, I'm just going to put a little blue dot there, relative to our new z naught, would be equal to the flow relative to the origin there. So really we've just translated in x and y, or on the real and imaginary plane, we just translated this flow over. And so what I can say is that the new phi of z is going to be equal to the original phi of z minus z naught. Okay, so I would take that original phi and do z minus z naught, and that would give me the new phi of z. Okay, so let's look at what this would look like for, just for example, we'll look at a source. So the original phi 0 of z, when that was centered at the origin, the equation we got for that was lambda over 2 pi natural log of z plus c. Okay, but when we translate that now, we get some new phi of z, and that is equal to phi naught of z, which is lambda over 2 pi natural log, and instead of z, we're going to put in z minus z naught, where z naught represents how far we have translated that. That's an imaginary number. It has both an x and a y component in there for both the x and the y translation, and then plus c here. Okay, so that's just one example of moving a source from the origin to some point z naught, and this would be the resulting flow field around that point, located when the center of that source was moved to this location z naught. Okay, so this was translation, and we can actually do the same type of a thing for rotation. So if we look at some type of a flow element here, again, I'll just draw a source, but what we want to do is now say, what if I rotated that source around? And so now this is going to be a little tricky to draw or to visualize this as a rotated, but this is rotated by, we're going to use the angle alpha. Okay, so now we're talking about rotation. So we're gonna rotate by alpha. Okay. And so what we'll find here is that the new phi of z is equal to the original phi naught of z, but we're going to multiply that z by e to the minus I alpha. Okay, and we would get there by the same logic that's saying, this point over here, the flow now is equivalent at this point over here where that's been rotated, from the original point. Okay, let's look at an example of this now, but let's use uniform flow because we'll see that that's really handy to check this against. Okay, so for uniform flow, our original phi 0 of z, in a previous lecture, I showed that if alpha is 0, then phi naught of z is just v infinity times z plus c, where c is, again, that complex constant. And this is for uniform flow, without any angle of attack. So it's just aligned there with the x-axis. And now, if we want to rotate that by alpha, then the new phi of z is going to be v infinity times z e to the minus I alpha plus c. Because all I've done here is plugged in or multiplied the z by e to the minus I alpha. Okay, so we just multiplied it there, and that's what we get here. And remember that e to the minus I alpha is equal to cosine alpha minus I sine alpha. Okay, so if we plug that in, we actually get that phi of z. Oh, I didn't mean to put a little z there. These phis are just the new phi of the rotated flow field is equal to, I'm just going to plug in the cosine alpha minus sine alpha instead. And what we get here is z cosine alpha minus I z sine alpha plus c. And we actually find that this is the same equation that we had before when we had the free stream at some angle of attack alpha. Okay, so what we've done here is not only can we rotate free stream, but we can actually rotate any of our elementary potential flow elements or any combination of them by simply plugging in this E minus I alpha and multiplying that by Z. Okay, so we can actually do rotation and translation at the same time. So let's see what that looks like. Rotation and translation. And let's do this on a doublet. Okay, so we've got the doublet, the original doublet equation when it was centered at the origin without any rotation. The equation for that was kappa over 2 pi 1 over z plus c. Okay, so now I'm going to rotate by alpha. And so I'm going to get this new, I'll call it phi 1 of z is equal to kappa over 2 pi 1 over, and now I'm going to take z e to the minus I alpha plus c. So I've rotated that doublet, and now let's translate the doublet. And what we'll get is our final phi of z is equal to kappa over 2 pi. And I'm going to move that e to the I alpha into the numerator because it's negative, so e to the I alpha over, and then instead of z, I'm going to put in a z minus z naught, okay? Where that z naught, again, is the amount that I've translated it in the complex plane. And then we've got a plus c here. Okay, so we can now take the derivative. So this is our final complex velocity potential, and then the final complex velocity is just the derivative of that with respect to z. And notice that z naught here is a complex constant, and alpha is also a constant. Okay, so when we take the derivative, it's actually pretty straightforward. We have kappa over 2 pi. We've still got e to the I alpha up there. That's just a constant. And then in the denominator here, the z naught is a constant. And so what we get is z minus z naught squared. And I have to put a negative out front. And so that's our complex velocity. Okay, so this is a complex velocity of a doublet that has been rotated by alpha and translated by z naught. So let's look at one last example here, and that is the flow around a circular cylinder. Okay, so originally that flow without any translation or rotation was phi of z equals v infinity, let's see, times z plus r squared over z plus I times gamma over 2 pi. And we're including circulation here, so I'll just say circular cylinder with circulation. We're including that gamma term. So gamma over 2 pi natural log of z plus c. Okay, so so this was the equation of flow over that cylinder, the complex velocity potential when there's no translation or rotation of any of the elements. Okay, so now I'm going to rotate this entire thing and translate the entire thing. And so you can see from the example above that what we're going to do is for each of the z's, I'm now going to plug in a z minus z naught times e to the minus I alpha. And that includes now the rotation of alpha and the offset by z naught. And so what we get here is v infinity times, and actually, rather than work through this, I'm just going to give you the final solution. We're going to find that some of these terms combine and into other constants that can be brought out here to the end. And so we can simplify the whole thing down to this final solution of v infinity z e to the minus I alpha plus I times gamma over 2 pi v infinity times the natural log of z minus z naught plus r squared e to the I alpha 1 over z minus z naught. And that's plus c, where this plus c is a little bit different than the previous one because we're going to have some other constant terms. You can see, for example, when we multiply this constant z naught by e to the minus I alpha, that's just a constant that will show up. So that's one of the things that gets added out here into this new complex constant at the end. But that doesn't really matter if we're just interested in the velocity, what that complex constant is. This is the new phi of z, and the new velocity then of z, the derivative of that is v infinity, and again alpha and z naught are constants, so what we get here is e to the minus I alpha plus I gamma over 2 pi v infinity. The derivative of natural log is going to be 1 over z minus z naught. And then we have, we're actually going to have a minus over here because of the derivative there. So it's r squared e to the I alpha times 1 over z minus z naught squared. And that is our complex velocity. Okay, so by swapping out for any z, just to kind of recap, for any z, we can swap that out for z minus z naught times e to the minus I alpha to include the rotation of alpha. So that's the rotation, and the translation by Z naught from the origin. Okay, so we can do that to any of these potential flows or any combination of these complex potential flows.